Another big topic with LTE, I think we're getting close to the, to the end here, is frequency reuse. So in Wi-Fi, you're probably very familiar with having to do careful channel planning to avoid co-channel interference because you start sharing capacity and decreasing performance at that point. And the reason for that in Wi-Fi is because you do preamble detection through clear channel assessment, and if you hear a preamble, you back off, you defer. It's what I would term blocking interference, right? If I hear a preamble, it's blocked me from acquiring the medium and being able to transmit. In LTE, you got to throw that out the window. Channel planning and design and frequency reuse are completely different. There is the interference coordination in LTE is non-blocking, which means two things. First, you see on the visual that LTE eNode Bs can actually sync up with each other and interleave when they're scheduling traffic to make sure that they don't collide, or they don't have collisions, right? So we can do a scheduling aspect to it to make sure to reduce that interference. But beyond that, if they do transmit at the same time, they can, it's non-blocking, and it just raises the SINR noise floor for, for that packet or that frame. So it's not preamble detection and deferral, you can still use the frequency, and depending on your design, how much signals overlap in those coverage areas, they can transmit at the same time, and it just impacts the noise floor, and potentially then adversely impacts the MCS and the data rate selection, right? So if I've got two eNode Bs on the same frequency that overlap to some degree in signal, and they're both transmitting to clients that are attached to them, they can do so at the same time. They both might have a little bit raised noise floor. They both might have to reduce their data rate going down to those clients, but they can still transmit at the same time. Very similar, like if you're familiar with some of the features in more modern Wi-Fi for RxSOP and things like that, where you're just ignoring interference. You're kind of doing the same thing here. You're ignoring it. Well, first of all, you're scheduling it to the best of your ability to make sure that you interleave them so that you can schedule those transmissions so they don't overlap. But if you're in a high enough congestion environment and that scheduling just is not possible, then you still can, to a degree, ignore the interference from neighboring eNode Bs and cells and still transmit with an impact to data rate. Yeah.
What's the latency situation between eNode Bs that have to coordinate or sync up? Do they need to be within a certain threshold?
So the question is, what's the latency target if eNode Bs need to sync up to do interference coordination? I honestly have no clue if there's a latency target for those on the back end for that coordination.
Yeah, I mean, for the TDD operation, like in CBRS, it's very tight. I mean, we're talking about, if I remember correctly, 10 microsecond or something of that nature. And they are typically, like outdoor base stations will be disciplined by GPS, right? Indoor, you can use PTP or other mechanisms when you have a master, timing master in the enterprise. So that works generally just fine. But then ultimately, they are very well synchronized, both operation on the downlink and on the uplink. So that's part of the reason where you can get really this kind of operation simultaneously on the same channel without going into listen before talk or other mechanisms like that.
Yeah.
So the eNode Bs need to be synced. So each eNode B can have a separate GPS antenna to sync it to GPS, or there can be on the back end, like in the enterprise, you may have a timing master, which is disciplined by GPS or any other source, and that can be the timing master for all the indoor eNode Bs inside the building. So that's more typical indoor deployment scenario, for example. For outdoor, you may not need it because each of them can have line of sight to satellite, right?
Yeah, so I think, one of the things that you might hear is that, another reason why LTE might be more efficient as a protocol and is because it has better frequency reuse characteristics than 802.11 Wi-Fi. There are carriers that deploy licensed cellular with, one or very few channels, and they get a lot of frequency reuse because they design it so they have minimal overlap between sectors, and when there is overlap, they can coordinate it very carefully for scheduled transmissions. So you can get a lot more out of less spectrum with LTE than you can with Wi-Fi, for instance. So that's why, like, when we're looking at 150 megahertz potentially in CBRS, that's a lot of spectrum for LTE. That's more than any carrier in the US individually has nationwide for their macro networks. I think I had a slide up yesterday that showed that. And a lot of that capability is due to this frequency reuse.
There's no concept of a clear channel assessment. Just assume the channel available schedules it if there's a problem.
Yeah, so the question is, there's no concept of clear channel assessment, correct? It's in control of the channel and it schedules transmissions how it wants, yeah. There is a concept of additional coordination for TDD LTE, like on the config profile of like the downlinks need from multiple eNode Bs. That's why I was saying you want all the eNode Bs in a given site to have the same config profile, because for that synchronization for interference coordination to happen, the downlinks need to happen at the same time and the uplinks need to happen at the same time. I don't know if you want to go into any more detail on that or if that's sufficient, but that's my understanding of it.
Yeah, you're absolutely right. I mean, for one deployment in one building, it will be like config 1 or 2, where you allocate maybe 6 out of 10 resources on the each frame for downlink and 4 on the uplink, but that will be all coordinated for that one network. But in another network, it may be more uplink heavy traffic, and you may choose to allocate more uplink resources than downlink.
Yeah, but they need to be consistent.
Yeah.
Does that make sense? It's a bit different than you're probably used to. So, we just start to think of the ramifications of this frequency reuse when you're doing, predictive design and channel planning and things like that of, there's probably, less strict requirement to have those channels completely non-overlapping and spatially separated from one another. But you still want to be careful about it because you don't want to decrease your capacity by increasing your signer, right? So you don't want to increase your noise floor still. So you do want to still do kind of the salt and pepper with the channels and get them spatially separated if you can, but it's not as disastrous if you happen to have some overlap. A little bit on 5G. We're not going to spend a lot of time on it, but some of the key features in 5G, you'll hear 3 different primary use cases for 5G mentioned. One is enhanced mobile broadband, which is really about increasing speed, particularly through additional spectrum and like millimeter wave, additional carrier aggregation with more radios being aggregated for larger channels. And you'll also see it for better uplink performance. So LTE as a protocol, you have that config profile for downlink versus uplink. It's fairly static in nature. 5G adds a lot more flexibility into that. So it's not only higher speeds, but it's more flexibility in you can burst uplink traffic in particular for a lot higher bandwidth. So that's one of the key improvements that's going to come with 5G. The other one is ultra reliable, low latency communication. This is more for edge computing, AR, VR, robotics type applications where we're doing a lot of advanced things on an endpoint device. It may need a really low latency link to something back on the infrastructure for compute processing and things like that. Because it can't be local, those devices will get too expensive to pack in a lot of compute processing power into every endpoint. So they want an ultra low latency link back to a local application server or something like that on an edge compute platform. That's one of the targets. So they're targeting, like today you might see with the LTE scheduler, it takes about 20 milliseconds from a latency perspective to get access. And when you're doing like a speed test or something like that, you'll typically see that amount of latency just to schedule traffic over the LTE scheduler. With 5G, the targets are attempting to get down to the 1 to 2 millisecond range as well. And then the third one was massive machine type communications. This is really around IoT, high density for IoT deployments in industrial, mechanical type of environments. So those are some of the key things to think about with 5G. There's a lot of hype out there right now, and it supports a lot of different spectrum bands as well. So in the US, for instance, a lot of carriers have focused on millimeter wave, which is high band spectrum, but it has very low propagation characteristics. So you would need really dense deployments of 5G new radio, indoors especially, to get that service. But it's great for marketing because you can market, really high multi-gigabit type of numbers because it's very high frequency, very high modulation rates, but it's typically like in-room only. 5G, it can also be deployed in mid-band and low-band spectrum. You might have heard like T-Mobile claiming the first nationwide 5G network because they're deploying it in mid-band. They can get a lot larger coverage areas out of that on their macro networks because it's mid-band spectrum. So it propagates and the attenuation characteristics allow it to go a lot farther. But then again, the downside of that is it's again, not nearly as high bandwidth as the millimeter wave stuff. So keep some of those things in mind when you're hearing about 5G. From a timeline perspective, we're looking at right now through 2020, mainly enterprise cellular deployments in CBRS using LTE. 5G radios are expected to be available for CBRS sometime in 2021, supporting release 15. Release 16, which is the next release with additional 5G capabilities, will be in a little bit later than that. So that's kind of where we're looking at. LTE today, 5G in about a year. Additional spectrum, so FCC is working hard to open up additional spectrum for 5G, not only from a licensed carrier perspective, but also from a shared spectrum perspective. So they've got a plan to, auction high-band spectrum, mid-band spectrum. They're making a big target for 5G, which is CBRS sits in. They're working on additional 2.5 gigahertz. They're also working on the band right below CBRS. There's 100 megahertz right below that is not highly used by federal incumbents that they're looking to do into shared spectrum as well. And here's kind of a global snapshot. You can see the US there. They're targeting 600 megahertz, 2.5 gigahertz. The 3.55 to 3.7 is CBRS. And then you can see they go higher up into some of the high band spectrum for the millimeter wave stuff. But that's kind of just a snapshot for your reference of 5G globally. I think we talked a little bit about, and maybe Mehmet can actually come up here and provide some flavor on global shared spectrum initiatives, because I know we're talking a lot about CBRS this week, but enterprise cellular as a market is bigger than CBRS, and it will be bigger. It's just a matter of additional spectrum opening up. So there's some spectrum already open in Germany. There's some in the UK. I know Europe has some proposals that they're looking at. So maybe if you want to just touch on that a bit.
Yeah, maybe first thing in US, there's a CBRS of 150 megahertz, right, from 3.55 to 3.7. But now FCC is considering the lower part of that CBRS band from 3.45 to 3.55, another 100 megahertz for this shared kind of usage. The next one is Germany. Late last year, they opened up 100 megahertz from 3.7 to 3.8. And their method is a little bit different. It's more old school. You kind of put your address and, send your application, and in a few weeks, you get your grant. And they have an interesting formula, like it's a function of number of years, how much spectrum you apply for, and also your use case is agricultural versus industrial. But at the end, like for a few thousand euros, you can get 100 megahertz of spectrum per year. It's a pretty good deal. UK opened up spectrum quite a bit, again, for private use cases. Similar mechanism like Germany. That one is 3.8 to 4.2. And then they have a few other chunks at the, from 2390 to 2400 on the lower end of the ISM band. Japan opened up some spectrum on millimeter wave. Again, these are all private enterprise type use cases. And mid this year, it's expected that they will open up at least 100 megahertz, probably 200 megahertz in the mid-band. Many other countries are following this. I mean, there are examples like Netherlands and other places are about to happen as well. So that's kind of the overall summary.
Yeah, so I think that, the big thing is don't just think of it as CBRS, think of it as private LTE and private 5G that's going to continue to grow as spectrum bands open up, just like Wi-Fi has grown into different spectrum bands as they've opened up.
Yeah, I mean, in this domain, US really showed leadership, I think. Many of the regulators globally has been looking at what will happen with CBRS, will it be successful or not. Now that it's kind of already commercial, I think all other regulators are now saying, okay, this is a model we can use in addition to the licensed spectrum.
Cool. All right, that's all we have on LTE. Maybe I'll do one slide on Celona solution, and then we'll get some hands-on with some iPhones. How about that? You guys ready for hands-on, probably? Yeah. Which one do I want to pick? Not that. Yeah, I'm just going to give you an overview of our architecture. So we have radios. We have both indoor and outdoor. These are the indoor ones here. They are 2 radio or 2 cell. We have outdoor ones that are hardened. You connect outdoor antennas and large sectors to, and you can get, all sorts of different antenna options. The Celona Edge is the implementation of the EPC and additional functions. So it's the packet core that has been completely rewritten from scratch to be written as cloud-native software, meaning it runs on Kubernetes, it's orchestrated, it runs each function. So I had the architecture with all those different functions, the serving gateway, the P gateway for packet gateway, the HSS, the MME. All of those functions are decomposed and implemented in containerized fashion as a microservice. And we can scale each one of those independently within the system. So if we're seeing a lot of data plane traffic coming through a specific EPS bearer, we can spin up additional containers for additional functionality in the Celona Edge, in the EPC, based on those performance characteristics. And they're also isolated and don't impact the resources of the other functions. It's all, our Celona Edge is mainly a software stack. We like to tout ourselves as mainly a software company. We do have hardware components for the radios, but we're mainly a software company. So that Celona Edge can run as VMs in a clustered fashion in an existing virtualized environment, whether that be VMware, Hyper-V, KVM, whatever the case may be. Or it can run as an appliance. You could buy, 1RU servers of your favorite brand, or we could, pre-deploy it on appliances, and you can get it kind of as a black box if you don't want to have to support the hardware either. The Celona Orchestrator, so before I move on, the Edge also implements spectrum management. So that's where it connects out to the SAS from the core. So we do all the SAS inquiry and grants for all of the radios that a packet core or Celona Edge is managing. And through our orchestrator and policy engine, you can map the eNode Bs to which packet core should serve it. So you can place these packet cores wherever you want. You can place it on premises at a site if it needs local traffic drop-off. You could place it back in a private data center. You could place it in the public cloud if you want. It's all around, depending on what application flows and architecture you need to support. And you can support multiple different of those within the same environment. So I could have a network with 20 sites where they all have local packet cores, and I could have some other sites that are for different purposes that all have centralized packet cores. And that's all managed through one orchestrator, which is the Celona Orchestrator, which is a public cloud deployed solution for management and orchestration, fully API driven as well, so you can program the network with DevOps. And that also is where you interact from a policy configuration perspective. You do your sites, your hierarchies, you do your QoS configuration, you do your subscriber management through there. Yeah, and that's the Celona kind of solution in a nutshell. End to end, you can get everything from us, or you can get a piece from us. Like if you want the core and the radios and you want to do your own subscriber management, you could buy a third-party subscriber management solution and tie it in.